Let's see here. Gotta turn off Bluetooth. Okay, so I gotta spam this share link everywhere. Okay, so I gotta spam this share link everywhere. Okay, so I gotta spam this share link everywhere. Hypnose. Computer check. There we go. Alright, I'll share that out a bit. Hypnose. Alright, I'll share that out a bit. Okay, so welcome my two viewers that are watching. So today we're going to be working on some byte addressable RAM in digital. So the idea here is I'm going to have a 32-bit CPU, and the CPU is going to be able to do things like store byte, load byte, store half, load half, store word, load word. And these are going to be they're going to have to be implemented in such a way that they're aligned. So if you think about it, let me pull up a graphic that I saw actually the other day. RAM alignment. So this is a nice graphic that I saw that explained it visually, but I don't know if I'm going to find it on a Google search. Probably not. No. Okay, so the idea here is if you look at the bottom 2 bits of an address in memory, if the bottom 2 bits are 0, 0, that means it's a multiple of 4. So if your number is a multiple of 4, it's a multiple of 4 bytes, you know you're loading a word, because a word is 4 bytes. Hello, MP. Is the video stream still working? It says it's not optimal at this resolution, but it should still be working, I believe. Let me just scroll through here and see what happens. I don't see it updating on my stream yet. Uh-oh. Oh, there it goes. Okay, no, it's good. It scared me there on YouTube. Let me get rid of that warning. How do I up my bitrate? Settings, stream, output, streaming. Where is what is the exact bit rate? I set it for quality. Apply. Alright, we'll see if that updates, gives me a better bit rate on the video. Okay, so yeah, the idea is if my address is, oh, here it is. Here's the picture. God, this is gonna suck zooming in on it because it's not a PNG, so sorry how blurry this is gonna be. I'll just try to center it on my screen a little bit. Okay, so the idea here is if you have a byte can be aligned on any of the low 3 bits of an address. So you can put you can ask for a byte anywhere in the RAM. So any address, you can ask for that byte at that address if it's byte address RAM. Now, if you're asking for 2 bytes, aka a half a word, or in my case, that's going to be half a word, yeah. So if you're asking for 2 bytes, which is a half word, it's aligned on the zeros when the bottom bit is 0. So 0, 1. On the bottom bit being 0, it's aligned. Then 2, you can't make it 2 in binary. It's 1, 0. So the bottom bit 0 is aligned. 4, you can't make 4 in binary. It's 1, 0, 0. So the bottom bit is 0, it's aligned on a 0, right? So if we shift it now by one address, we're now misaligned. So if you have 2 bytes, you're going to have to be aligned on a 0, whereas a single byte doesn't have to be aligned on anything. So now if you follow this pattern, then on 4 bytes, you have to be aligned on 2 zeros. You have to be aligned not just on 0, 1, but you have to be aligned on all 4 possible combinations here. 0, 1, 2, 3. So you need four outputs. The only way to get 4 outputs is with 2 bits, and you need to be on the low end of those there to be aligned. So when you're doing byte addressing, if you have byte address RAM, you can search and read and write a byte anywhere. On halves, they can only be aligned on the 0th bit being 0, and on words, they can only be aligned on the 2 bottom bits being 0. So that's going to be our condition on how we're going to generate this memory. And then, of course, they show 3 because then you can go, past 32 bits with 64-bit systems. So, welcome viewers. So yeah, now what we're going to do, now that I kind of explained what we're going to have for control, we're going to need to define some inputs and outputs and kind of think through this as we go, because I am not prepared at all, so we're just going to kind of wing it. So what are we going to need? Well, obviously we're going to need an address. So I'm using 32-bit addresses. And the idea here is each one of these RAMs, why is that not set for 32 bits? Can I not set 32 bits in there? Okay, digital's limit is 24 bits. So we're going to use 24 bits. So each one of these is going to hold 8 bits. And this is how we're going to force alignment. So we're going to say, if you write a byte, you can write a byte to any one of these addresses. And this is going to be the 0, 0, 0, 1, 1, 0, 1, 1 address. Or you can say, I'm going to write a word or a half word to either these two or these two, but you're not going to be able to write a half word to here or a half word between these two here. So you're only going to be able to align it like that. And then a full word, you're only going to be able to write across all 4 of them at a time. So that's how this is going to work. So we're going to have an address which is 24 bits, and we're going to need a splitter because we're going to need to look at the 2 bottom bits. So input is going to be 24 bits, and the output is going to be, well, we want the bottom 2. I don't remember if it gives me the top or bottom there, so, but we'll try it, and we'll see what happens. Okay, that worked. Perfect. So what it's doing right now is it's giving me, oh no, that's not what I want. Wait, is that what I want? 0? Yes, that is. Yeah, 0 and 1 are the 2 low bits, and 2 through 23 are the top high ones. So I still get my address out here. So I'm going to use this here, but I'm basically just going to be looking at these 2 bits here and throwing away the top ones that I generate. Like I'm just not going to be looking at the top ones there. So now we just have this 2-bit bus here that's going to tell us what we're doing based off of if we're reading or writing. Also, the component RAM that I used, if you guys are trying to build along. Yo, what up, Dark? So the RAM we're using, by the way, is this block RAM separated port. So if you wanted, you can export this to an FPGA. Otherwise, you can just use the separated ports RAM here, like that. So now we're going to want to have another input. I'm going to call this a data. And it's going to be 32 bits. Now you can think about it like this. If I have 32-bit data, I'm expecting the CPU, if it wants to write a byte, that byte is going to be given to me in the low 8 bits of this 32-bit value. If I'm getting a half, it's going to be the low 16 bits, and if I'm getting a word, it's going to be all 32 bits. And that's the assumption that's going to be made here at this data input. So to actually now parse this properly, we're going to need controls, like I said, we have load and store, and then half word and byte, or byte, half, and word. So I need to select byte, half, word, and then load store. I'm trying to figure out what's the best way to have these inputs, because you can have load byte, load store. You can have each one separate, and then have to do decoding on. You know what? Yeah, let's do each one separate. Fuck it. How do I actually? No, we'll have load. Yeah, that will. Never mind. We'll do it separate, and then externally the logic can put both lines high if we need to. So we'll just do Control C. Excuse me. What the heck? Control C, Control V. Okay. So I just want to grab like load and store. Okay, so if store is true, then then the stores will be true down there, and if load is true, then we're gonna have to put mocks on here that read this out. But we'll worry about that in a bit. Okay, so what we want to do now is we need byte, half, and word. Components, IO, input, byte, half, word. So then you could say load and then byte, or load and then half, so it'll be only one of these is true at a time and one of these is true at a time. And you'll need both, one set of these and one set of these on at a time for something to work. Okay, so now if we think about this, we're gonna have a decoder here. So plexers, decoder, oops, components, plexers, decoder, place it, right click, rotation 180, okay. Flip selector position, nice. And number of select bits is 2. Oh, why did I flip it? Oh, I shouldn't have. Keep it the way it was. That was dumb of me. Okay, so we're gonna take those 2 bits, and now we're gonna have all these conditions that can come out here and control things. So basically, we could say if the load bits were 0 here, then that means you can then load. You could then, if this is true, then the byte is then this is allowed. Right? Because actually a byte will be allowed on any. Okay, so here we'll have an enable signal. We'll have an okay signal. The components, logic, and we're gonna make that not fat. And so this is gonna be the byte okay. Whether you're loading or storing, this is gonna generate the okay signal. So you're gonna have components, logic, OR gate. I'm gonna get rid of that ridiculously wide shape, and we're gonna give it 4 inputs. Okay, and we're gonna basically move this out of our way. And what would be the best way to do this actually? I'm trying to think. How do we want to do this? So the address, the byte can be aligned no matter what, so we don't even have to disable it. Like the byte is just good. Like why even fuck with it? Like if you do byte, no matter what the address is, you can write a byte there. But the half, I shouldn't have Control Z. I'll just Control X, Control V, and put that in for the half. And we'll say the half is allowed to be written when you're oh yeah, and we'll just give this 2 inputs, and we'll say when you're aligned on the 0 or the 2, you can write a half or read a half. Okay, and then now on the word can only be aligned on the 0. And can I make this look a little less shitastic? Probably. Yeah, something like that. Cool. Okay, so the logic so far is if the bottom 2 bits of the address have aligned or don't align on anything, who cares? You can write a byte or read a byte. If the bottom 2 bits are 0 or 2, then you're able to load a half. And if the bottom 2 bits are only just 0, then you're able to only write or read a word. Okay. So now that we know this, we now have like controls for this. So we will have an AND gate. Control C, Control V. We'll rotate this 90 degrees, hopefully. Nope. 270. Okay. And we're gonna have like a store, and we're gonna say the store is true on that particular part of RAM when we're using the condition that should write there. So let's get some text in here. Components, text. So we're gonna call this. Oh, can I just give them these labels? Yes, I can. Okay, so 0, 0, 0, 1, 1, 0, 1, 1. Okay, so now you can see this is true when the bottom 2 bits are 0, then 0, 1, then 1, 0, and then 1, 1. So we're going to be using these to say how we're going to be controlling this. Okay, I gotta connect these up. So if you're doing a byte, then the byte will come here. Oh man, we have to. Okay, wait. So we're gonna have to let me bring the store input down. Okay. So if you store byte, you're gonna have to store every single one. And then if you store half, you're only gonna be able to store these two or these two. So I need how many? I need components, IO, no logic or rotate. I think 270. Get rid of that stupid wide shape. And 4 inputs, I think. So maybe this is what I need? So the idea here is we will be able to tell it when to store, and then we'll do the same logic on the reads. So a byte should be able to come down here. Like that. So a byte wait a second. No. Uh-oh, why isn't undo working? We're going to store there. Oh, but for byte. Oh, okay. How do we? Okay, so this is going to tell us which one we're storing a byte to. let's think about this. Let's just wire it up so I can think as I wire it up. Sometimes that just helps me think about the problem at hand here. So right now, if you put in, say, a low 0 address, the decoder here will tell it to write to this one. So if we have a 24-bit address and you're dividing it by 4, that's like shifting it left, shifting it right twice. So you have 22 bits left. So these need to be 22 bits. That, or I make this 24 and then add 6 bits. Oh, that's what I can do. I can add more addressing out of this. Yes. So I'll make this 26 bits. Input 26, output 2, and then 24. Okay. Cool. So what I did is, since I'm limited to 2 to the 24 in here, bytes, I'm saying I have 2 to the 26 amount of bytes I can actually use by splitting them up, because I have 4 different spots I can write a byte to. So I multiplied my amount of memory by 4 by doing this. But anyway, back to the problem at hand. We're going to only store to the one that the address comes into true for a byte. So we need inputs. We need 3 inputs on this. And the third input here is going to be I see. All of them get true. All of them get true for a byte. Wait a second. This file open. Byte address memory, yes. Open file location. Alright, I made a byte addressable memory once. Oh, is it not going to open? Okay, it's in documents. File, open a new window. Documents, what was it called? Jarvi 36. 12. Okay, so this is how, oh god, this is messy. But this is only using 16 bits, so I had half and a byte and a word. So the idea was, where did I look at the address? I looked at the bottom low bit and was able to, alright, fuck, that's fucking, see, I didn't want to look at this because this is sloppy and I wanted to do this a better way. Yeah, this is gonna be a pain in the ass. Oh, that's right. Okay, okay. God, yeah, all of this is a pain in the ass to consider everything for. So one of the first things we need to do is take this data bus. Wire splitter. So our data is 32 bits. And we're going to output 8, 8, 8, 8, 8. Okay. So now we can take the low byte. So components, fuck. Okay, actually, no, that's fine. All right, so the low byte. Actually, fuck, this is complicated. So the way this is gonna work, let me get a text document in here, and we'll write it out so we're not lost. Advanced, whatever, font size. So we're gonna want to have. So let's say you have address 0000. Let's actually lay this out like this: address, data, and see what happens to the press. Okay. Oh, that's huge. Okay. So how am I going to represent this? So we'll have 1, 2, 3, 4, and data of FEDC. Something like that. Okay. So let's think about, if we have address of 1, 2, 3, 4 in hex, these are hex values, and we're doing a byte. If we're writing a byte, we're going to be grabbing the C here and writing a byte to address 1, 2, 3, 4 in hex. Let me make this a little bit easier. 0, 1, 2, 3. Okay, because that's a lower address. This is in my way too. So when I'm writing a byte, I'm saying this data can come. Okay, so this. Oh, I see. Okay, so when I write a byte, we're going to have this data that can come into any one. When I write a word, it could be I'm putting the low byte there, and the high byte would be there, and the low byte would be to my right, and the high byte would be there. And then if I was writing a word, the third bit would have to be here, and the fourth would have to be here. 1, 2, 3. So I think that makes sense. So now this is my data inputs to here. So now I need to mux them. So components, plexers, maybe a demux? No. I wanna, yeah, I'm gonna need it. Components, plexers, multiplexers. Rotate 90. Nope. Rotate 270. There we go. Okay, and now we're gonna have to space this shit out. This has to be 8 bits. Components, wires, ground, 8 bits. Okay, and now we need components, logic, or rotate 270, learn the hard way, 3 input, 8 bits, 3 inputs. Okay. So now we still need to worry about the address that comes in and tells it what it's going to be. So the address that this sees is the top, is these bits here. Okay. Right, because if the bottom 2 bits tell it where to write the byte to, the top 24 bits have to tell it the, oh, is that right? 0 to 20, yeah. The top 24 bits have to tell it the address of the word. So these all have the same word address, but the bottom 2 bits differ. That's why we labeled them like that. Okay, so now we're basically going to have, if this is true, this is load byte, this is load half, and this is load word. Load byte, load half, or byte, half, word, and that's going to be these controls up here. Okay, now we're getting somewhere now. We're getting somewhere. Okay. It's not just me rambling anymore, so my 6 concurrent viewers, you can rest assured we're gonna get some logic done here. No. It's actually pretty good having 6 viewers, damn. I'm happy with that, thank you guys. Don't forget to talk in chat if you guys are lost, don't know what I'm doing, think I'm doing something wrong. Whatever, I'll listen to you. Or I'll hear you out at least. I don't know what the fuck I'm doing here with this store shit yet. I don't know why I'm carrying this grandfathered shit in. Hello, David E171. Nice to see you in the chat. Alright, so I'm just going to work on the data in for now because I seem to understand the logic that needs to take place, at least in terms of commands. For anybody that's still following along, or like trying to follow along, I'm trying to write this. I have a 32-bit data coming in, and depending on the condition of what I'm doing, it needs to grab bytes from that data in different spots. So I'm gonna just basically rip this out, perform a little surgery. Well, not rip it out, just Control C and Control V, perfect. And I'm only gonna need 2 of these guys now. So I guess I'll get rid of this guy, the 3rd leg here. I'll move this guy over, just out of my way. Boom. Okay, Control C, Control V, and 2 inputs. So, if this is yeah, I'm gonna get rid of this crap. So this is going to be word, this is going to be half. Oh, god damn. Okay, phew. I made it out. So, word, half, byte. Then it's going to be half and byte. And now we just got a little bit more to go. Control C. This is also going to be half and byte. Actually, no. Yes. But it's the top. It's the top 8-bit. Okay, yes. Data in. There we go. And then obviously this last one is just going to be the only data coming in. Okay, so this is load word, this is load half and load byte. And then this is, how do we follow this? God damn. This is going to be loading byte. And this is loading half. Oh, did I build that backwards? What the hell? This is loading byte. Ah. Oh, okay. Yeah. I said that backwards. So this is loading in the byte. This is loading in the half. And this is loading in the word. So we have byte to byte to byte. So now if we follow this, this should be grabbing the top one, and this should be grabbing the top one. Nice. And then this should be the top one, yep. So yeah, you'll only ever be able to write a byte here. You can't write a word. Oh no, you should be. What am I doing? Yeah, you should be able to write a word. Oh no, yeah, that makes sense. You can write a word starting at the low bits there, and it would take all the way up there. So you can only do it 0. Okay, no, that's fine. I thought I got confused there. Yo, what up, Slick? These are OR gates, not XORs, but yeah, close enough. God, this is confusing because the most I've done last time is just byte and half. So now I'm doing a little byte, half, and word. This one is pulling from that. Oh, fucking Christ. So this is doing, I should be putting 8 through 15 out there, and then 0 through 7 comes there. I don't think that's right. let me think. If we're saying load word or store word, if we're saying the data in is allowed to be a word, so this is storing. Yeah, I haven't really fucked around with Unreal Engine at all. So if I'm storing a word, I want to enable this to take this one. So this is word. I want this to take this one. I'm controlling the data going in. So I can write a byte of data to any of these. I can write the low byte there, and then the only thing that would be allowed to come into here is then the high byte. So this here would be saying load half. Load half. And then this is saying load byte. Can I label these? No. Oh, fuck. Load byte, load byte, load byte. Data going in there is the byte. So this here we'll put the low byte. Okay. This here we'll put 8 through 15 either there or 8 through 15 there, right? 8 through 15 there. And 8 through 15 there. Okay, cool. So 8 through 15 can go there, or 8 through 15 can go there. The only place this could go would be here. 16 through 23 should only be able to make it. Okay. So my logic is right here. I keep confusing myself as I think through this, because as you can see, it's quite easy to confuse yourself. So this one, when we're allowing 8 through 15 here, we're also going to have to say it would also be possible for 8 through 15 to be allowed through over here as well, which would be this guy there, because that takes 8 through 15. And then this one takes 16 through 23. That's only load word. So that's load word. And then this one takes, so that's load word. Okay, so components. Get some text. Half. Byte. Okay. So what this does is it just splits out the data. It's not parsing the addresses or doing anything with addresses. This is just parsing in data from the input. Hi, David. Yes, yeah, I think, right. So my logic does make sense on what would accept what. Yeah, okay. It's nice to have other people just to talk it through like that. Yes, thank you for confirming. It. I think that would work. We're gonna find out, I guess, right? um, so now we need to then check the boundaries on which we're aligned over here. Okay, so let's just pull this back a little bit. Let's just cheat and do that. Okay. So that is clearly only for storing when we're that this is going to come through here and affect the data in. Now we want to be able to affect the data out also based on those conditions as well. So now if you think about it, instead of doing the opposite here where we take an input and of 32 bits and we split it out into 8, now we're going to have an input, 4 inputs of 8, and we're going to have to split it in to a single 32-bit. I guess I should make this data and components IO output data out. I'll make that 32 bits. Oh boy. Okay. So now we're going to have to do the same thing. I'm going to grab these. See how close can I? Oh, I'm probably not going to be able to stack them that close together. Maybe we will. Okay, and we're going to say this data coming out this is going to be a little bit tricky. Okay, first of all, there's no reads on this. So all the data is going to come out. So immediately we need flex radius. $32 bits. Oh, can't forget that there. for symmetry's sake. And that's 32 bits, I think. Oh, that ground needs to be made 32 bits. Okay. So if we say read, this would be the read signal. Alright, if that's the read, then we're gonna have to tell it like what to read, a byte, half a word, and then where to put it on that bus. So if we read a byte, we got to put it down here. So so when you read a byte, you're going to put the address in. And you're going to have a demultiplex. Okay, so instead of a multiplexer there, now you're going to have a demux here. Components, plexers, demultiplexer. Or no, you know, you'd have components. You could use a mux. Fuck. So it would have 2 selector bits. Oh no, you'd have, okay, 32 bits. Like that. Yeah, okay, so it's going to be slightly different. So let's think about it. If you load a byte, oh, maybe I don't need this double redundancy. So, oh, so I have to look at the is that right? So if I select a byte, I need to look at the bottom 2 bits and it will tell me which one to grab. So, yeah. If I'm telling it to load, okay, so I need AND gate components, logic, and okay, so we're gonna say fuck. What? Zero. One, 2, shit. So now I need these signals too. So if I say, if this is true, I'm going to enable the data. Fuck, another complication. So let's think about this in another perspective. If I'm going to say, read a word out of this, this has to go to the top. All right, so let's start with word. Let's start with the easiest. So when this is true, let's set this up how I did in the other one. When word is true, this is just going to come. Each byte is just going to be able to come to its own position. Whereas if we're doing byte addressing, okay, and then if we're doing half, we can say that I think that's the possibilities there. Does that make sense, David? So if I think this out loud, so the reverse logic of the input is, if I'm asking for a byte out, I can get a byte out of this one, this one, this one, or that one, and I have to put it at the low spot. If I ask for a half, I can get the low byte here, and the high byte would have to be, say, this bit, or the high byte would have to be here, and the low byte would be there. So that would bring the low byte over here and the high byte here. And then if I'm writing a word, the only way to get a word to the output is that 1 0 goes there and 1 1 goes there. So I think that makes more sense. And so this is where I was coming from with my my multiplexer crap. And that's why I thought I knew I was going to need 4. And if we grab, see, so these are all bytes, remind you. we still have to worry about the addresses. So right now I'm just focusing solely on, because there's a lot of things to focus on when you do byte addressable RAM, both the address and the data itself. So right now I'm just focusing solely on the data side of things. Like if I'm writing data, it knows where from the bus to pull it from. And if I'm reading data, it knows where on the bus to put it to, depending on the type of data I'm reading. But I've yet to actually start modifying how the address works. Yo, what up, Bear Slicer? Nice to see you. I'm gonna take like a 2-second break, refill my bong, take a fat rip, and then continue working through this. Because I think I see now what I have to do. And I really appreciate David being in the chat and thinking through this with me. It's nice. Is there any questions from anybody on what's going on so far? Or because David seems to understand basically what's going on. Looks like my stream is about 30 seconds behind. Maybe 15. Yeah, David, this is my first time building byte addressable RAM for 32 bits. The biggest I'd known this before was for 16. Yeah, it is neat trying to think through the logic problem, but it's also like trying to reduce like the logic to being as simple as it can be. Okay, so now we're going to need 4 inputs. Okay. So the low byte can get data from grab data from any of these depending on what it's told to do. I kind of want to break this out a little bit. If I angle this, I can then get some buses out that I need out. Bus it down, Tatiana. All right, I won't say that again. Yeah, so now I can get those buses out like that. Okay. Okay, so now similar to how we did this logic up here for the data in, we're gonna have to do similar to this for the data out. So we're gonna say when we're reading, so it's gonna be the opposite of the input, whereas the byte could go anywhere, and it came from the zero input here. On this one, the byte can come from anywhere and has to go to the 0 input, so it's the opposite. So since the byte one here didn't have any logic coming off of it, the word one here shouldn't have any logic coming off it here, right? So the way we can say is the bottom. Which one? So word is the bottom one here. So we could say when we're doing load word, we're just going to take. When we're doing load word, we're going to take this one. Yeah, I think so, David. Isn't the basically store splitter logic in reverse? So 0 through 7 can get from any RAM node. Yes. Right. Oh, okay. So 0 through 7 can get from any, right? That's why it's like that. 8 through 15 can get from 0, 1 and 1, 1. 0, 1 and 1, 1, yes. Yes, okay, yeah, that's what I have. Okay. But now when I load word, what does my load byte here do? My load byte just comes into the single. Oh, okay, let me set up the muxes on here before I get too far ahead then. Wait, this is going to be so now we have to think about it in terms of this address again. Yeah, so let's. So when you're doing load byte, I'm going to set this up. So when I'm saying load byte, it could take any one of these 4 addresses. That's a pain in the ass. Okay, Control C, Control V. Okay. Sound like I feel like Little John. Oh, okay. so many control signals that can be generated though, because think about it. So David, this is what I'm struggling with internally. So on the zero, all the ways to populate data onto the zero, the low 8 bits of this bus, right? You can read a byte from any of these, and that would generate data onto this. You could generate a half word from this one, and the low word would come onto there, or a half from here, and the low word would come onto there. Or you could read the full word out, and it comes onto there, right? So I need several ways of controlling this. So I need like an OR gate on each one of these mux inputs here, which just blows up the complexity of that. Yeah, how would I start listing that? Fuck, it's too much to think about. I just want to build logic. So this is reading individual bytes. Oh, I see. Just making more inputs on this. Make it 7. Okay. So you're going to be able to say read any one of these. And then what else could you read as a 0? You could read that as a 0. Yeah, that's it, right? You could read each one of these as an individual byte and put it on the 0. Oh my god. Fucking Christ, this is a pain in the ass. I don't like my way of approaching that. Right, but then I'd have to drag these button control lines out before I forget about them. Okay, yeah, good point. Let's try to use these without putting redundant logic in. Just want to see all my signals and see what I have left here. Okay, let's think. If I'm reading a word, so if word is true here, if this is true, if that's true and my address is aligned on 0, okay, so yeah, we're gonna work through the logic here like this. So if this is true, I need to replace that gate with an AND gate, not an OR gate. Just using it for its position. Okay, so if we're trying to read a word and the address that we're reading from is aligned on the 0, we're good here. So if the address is aligned on a 0, this is true, and it will mean connect it'll mean, I gotta bring this down a bit. Let's say to that. Then to connect this one here, we're gonna say grab that. Definitely gonna need an OR gate though, for sure. Just not that many inputs. I'll put 3 on it just in case. Maybe I'll need less, maybe I'll need more. Okay. If this one gets read, it'll come to here. Yeah, I guess I'll put a mux. Something like that. Okay, so let's see if that makes sense for now. Just for reading out a word. If the word is true, and the address that you're inputting for like reading the word is here at the 0, that means you could read this byte, this byte, this byte, this byte, and put each one in their respective bit positions. So that means when this is true, you're going to read this one here, and it's going to come to these low 8 bits. You're going to read this one here, which comes up into here and go to those 8 bits. This one here into those 8 bits, and this one here into those 8 bits. Okay, cool. Alright, I'm just focusing on the data, not the address. I don't get myself confused. Okay. Where the data should appear on the bus. Okay, so now let's look at half. If you write a half, a half can be aligned on, just like we did up here, the 0 and the 1. So half can be aligned on with the 0, the 0, the 2, sorry. 0, 1, 2. So Control C, Control V, Control C, Control V. And so when a half is true, the data yeah, okay, so I am fucking it up. So right here is where I'm fucking it up. You see how I'm just bringing it over to its respective one here? I need to tell it, based off the 0 or 1, is the data going in these two or is the data going in these two? Oh, I guess that's the store. I can enable that with the store. And I can control that with the load here too, and just keep it generic like that. And say if the load, and look at the, if it's load, if it's load half, I would have to know to load either this one or this one. Okay, yeah, or store half. So let's half. Okay. So by keeping track of that like that, when we go to this half and we say here, instead of doing this OR gate here, we're going to have a second AND gate with the same condition there. This here OR gate is going to get removed, and we're going to say the 2 is going to come through here, and the 1 is going to come through there, because that's the 2, or and the 0 is going to come through there because I said that's the 0. And now the half, boom, like that, and we just delete that stupid bus, but it makes us have to do that, but whatever. Okay. So now the store half will do that. The byte yo, what up, implicit? Oh, I guess I didn't have to do that up on this one. I really only need this on the loads. Control plus click. Oh. Gotcha. Thank you. Yeah, I guess this is really only an issue. So when load is true, we're going to say all of those get true unless control click delete. Thank you. Control click delete. That looks like shit, man. I can't understand. There. Am I okay with that line just running across that? Sure, fuck it. I think I'm gonna stop on that logic for a second and think about this, because let's think about the address. Where's the address coming in? So how's the address work? The address is controlling which one of these oh yeah, okay, so I am kind of doing address stuff as I go along, duh. Alright, because... Yeah, what up, Nano? Yeah, this is a pain in the ass to think through it, Nano. You're welcome to stay and help think through the logic. So I give this an address. Let's say I give this the address. Let's stop working hex and let's say an address of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Okay, there's 26 bits. So I'm going to say, we give it an address of, say, 7. If I say an address of 7 comes in, what is allowable to be written at an address of 7? Only a byte. So let's see what happens with my current logic. So it says that it sees that these bottom 2 bits are 3. And 3, well, it won't allow a half a word to be written, so only a byte would be able to be written. And it would say write a byte into all of these. What I'm getting confused about is store and data in versus load and data out. That's what I'm getting confused about. So I'm gonna, because this store pin says if this input is high, when the clock becomes high, the data is stored. So on the rising edge of the clock, it'll store data. So what data do we want to store? Well, we need to tell it based on the address where it's being stored. Or no, maybe I was just thinking, or maybe I can just make it so store is just true. When store is true, the data will just go to the proper thing based on the address coming in and the type of condition to be done. So I tell it store byte, it'll put the store true on all of these and arrange the data so that the byte goes to the right one based on the input. I think maybe that's the way it should be done. So like, let's say we had store like that. And let's say we had to load like this. Because there's no load pin on these, so I just had to put a mux that would load them out. So now I'm going to have to redo this a little bit. Oh, true. Okay, David, that's a great point. So if there's 0 at that, it's just going to write zeros into there. So it's... That's true. That's very true. So, okay. So far, this arranges the data. So basically, if you were to write address 000, or all this with the low ones being high like that, it would see this here. So you see how there's 24 address bits? And so this is like, if all 24 of those address bits are 0, then here's your first word in that. Here, let me get Excel, maybe that would be the best way. So let's say, how do I want to represent this? 0, 0, 1, fuck. Format. Okay, where's just plain text? Okay, so basically, so you can think about it like this. So if I have 4, each one of these can store byte, and I enter address 0, I can store a byte at address 0, or I could store a word at address 0 through 3. I could put a whole word there. So each one of these is either a byte, or there's a half and there's a half, or I have one word, like that. Half, half, word, like that. So that's what I'm trying to figure out here. So it's the low two bits. The low 2 bits tell you which one. So you see here 0, 0, 0, 1, 1, 0, 1, 1. So the low 2 bits of the address come in here. So, okay, so I see. So if I'm writing a byte, store would be true for the decoder address here with store byte. Okay, okay. Components, AND gate. So I'm writing a byte. Okay, so I could say Control V, P. So we're going to take each address and we're going to say if it was 0, 0, say for instance the low 2 bits were 0, it would come over here and it would say this would be true when I'm loading byte. So this would be the load byte. So that comes from that right there. And whatever byte I'm loading, only one of these will be true at a time, and it would only ever put one of these stores true and write the byte. So the data theoretically doesn't need to be super conditioned, as long as that byte is on the low 8 bits of it, which I'm not doing any of that stupid conditioning here. Oh yeah, I am. I'm saying okay, fuck it. We'll just keep working through with what I have. So that'll make store true. The other way to make store true is store true for all of them would be a word. So I'm going to need an OR gate with 3 inputs: component, logic, OR gate. Three inputs, and we'll get rid of that wide shape. For node 0, 0, let's think about this. For node 0, 0, store when address 0, 0, when the low bits are 0, 0, and the byte or half or word is true. Right, so the thing, byte or half or word is true. That's my triple OR gate here, so I think we're on the same. Ooh. So now, when we're doing storing a byte, or a half, sorry, the half, let's just bring that in. The half will be able to either store, if it's, the half will either store these two, both of these two will become high, or both of these two will become high. Depending on if it's 0 or 1. So I think I can, instead of having the AND gates down like this, I can fit into the side. So I could say, we're gonna, if we're doing store byte, or store half, then we'll store the top. We'll store to the bottom ones if it's 0 was true, and we'll store to the top if 2 was true, like that. And now if store word, so now word would just connect all these guys together. Hold on 1 second, let me just finish this logic and I'll get to your comment there before I lose train of thought. So this is for word. So when word is true, it'll store data to all of those, and the data going to them will have been separated properly already. All right, so now what are you saying about? I think it would be best to have the store AND gate as the last gate before it gets into the RAM node. So the store AND gate. I don't know what store AND gate you're talking about. I know we're a few seconds behind in lag. Which are you talking about? This one that I just moved? I'll wait a few seconds so you can. So the stream will catch up and I can see your answer. In the meantime, I'll clear my bong. I'm not sure which AND gate you're talking about is duplicate right now, unless they're ones that I plan on getting rid of already. David, you there? Oh, I was confused about the AND gates you already have, but I meant the AND gates that would connect to your ANDs and ORs and the store input. Oh. Yeah, for one thing that can help clean this up is make that wire look better. That clean that up a little bit. I just want to make this look a little cleaner to follow. Because only ever one of these will be on at a time. Oh, fuck. One thing I didn't think about, though. Okay, so one way to do this now is make each one of these triple inputs and then connect it with my store input. Or just make it, put another AND gate on each one of these and connect it to store. So when store is true and then byte is true, then it would go do the right thing. But it can only happen on store, like it can't happen all the time. Like it only should happen when store is true. So I need to. I like that trick you showed me. Just gotta learn to use it more. Ah, okay. Okay, that makes a lot more, yeah. You were one step ahead of me, damn it. Yeah, see, so you do know what you're talking about. I want it to look somewhat uniform. Shit. God, this shit, like, they have, imagine if they just put a freaking byte addressable RAM component in and we didn't have to deal with this shit. You could put it either with the byte half-word inputs. Oh, like where I have them there. Or just before the signal gets into the store of the RAM nodes. Oh. Yeah, I could have gone. Would that make it easier to read to somebody trying to figure out what's going on? Or is this clear because it's like tapping off the byte half word inputs and saying store byte half word and then telling it what to do? I don't know what would make more sense to somebody reading this externally. But that's true. It would functionally be the same and the delay would be the same. So it's just like a designer's choice. I'm just gonna pack my bomb real quick. Yeah, I think either is probably fine, but I wired it up the way I did already, so I'm gonna leave it like that. Plus, it kind of looks kind of simpler in terms of fitting all the gates where they need to be. Is this runnable right now? Oh, I can't have open inputs on muxes. I'm kind of debating on just getting rid of this real quick. Right here? Yeah. Can I run? What did that say? Oh, I need clocks. Let me control Z. Oh, okay, yeah. What? Oh. I have to get to the point where it's like running and then I can delete that shit so that when I want to undo it, I don't undo the fix that I needed to make my circuit work. God damn it. Oh. What we'll do is we'll just delete that. Okay, so now that that's working and I want to be able to see what data is coming out, I'll just put some buses here. Okay, so now let's see how this works so far. So yeah, let's put in an address example of a 7. And we're going to put in data of F0 E1 what would be the, oh no, we'll just count up in hex. 1 2 3 4 1 2 3. Oh, it's 32 bits. 8. Yeah. 1 2 but I'll go in the reverse direction like this. 8 7 6 5 4 3 2 1. So 1 2 3 4 5 6 7 8. Apply. Okay, so each byte is a different input. So, or sorry, each nibble. So a byte is going to be like 2 1 4 3 6 5 8 7. So one of those bits, one number there is a nibble. 2 of those together is a byte. 4 of them together 16. All 8 is 32 bits. Okay, so if I'm saying now that address 7 comes in, it's telling me that address 7 is to write to this top one here. And it's also saying that the address coming in here is a 1, which is nice. We're at the first page of memory at the top bit, top selection. So I think that's right. So if I were to say store a byte there, storing a byte does what? What is on this bus? 21. So I'm saying store the low byte. You're right. If I take a byte, it's going to read this. If I take a half, it's going to read the bottom four numbers. And if I take a word, it's going to read all 8. So it's going to take that 21, and everything else here is zeros because it didn't take it. It didn't take 43. It didn't take 87. So now that 21 comes down here as data in here at address 1 in the correct RAM bank. So this is working so far. If I were to now say store, very nice, the store condition comes on, the data is still here, and the address is still 1. And now all I have to do is clock it here. Boom. And now since the address is still coming in, the address 1, why did the clock? There it goes. It's high. Oh, the block RAM, the output's only available on the clock being high? Okay, no, it's just a weird glitch, I don't know. It's there now. Okay. Now I can go back and put in just like zeros again, clock it, and now, what the fuck? Why does it have to be like clocked twice? Help, documentation, Control F, block, block RAM. It doesn't tell you what it does. I don't know why it's doing that. Let's try this again. Data in. 876544321. Address. We'll put in 7 like our example. I will store byte. I will say byte, and I want to store. It comes true here. That's a 0. So this goes high and goes low. It's a 0. Goes high, goes low. It's 21. Yeah, it needs 2 clocks. Like, what the fuck? Okay, we're gonna change to the RAM that we're using. Logic, memory, RAM. I'm using this separated block RAM, but I don't like that it's being stupid like that, so we're going to rotate this 90. Oops, rotate that 270, I guess. So that's in the same spot. The store and clock need to be shifted over a little bit. We're going to have 24 address bits of 8 data bits. And now these have a load pin too, which is nice. I'm just gonna like, oof. Okay. Okay, so now we'll just put a make that load. Yeah, I don't like that it takes 2 cycles. That's not acceptable. Maybe it's a bug, I don't know. But I'm switching RAM models. Let's see what happens. Components, IO output, rotate 90. Fuck. Nope. Rotate 270. Okay. And then number format. We'll display this in hex. Yes. It's only going to make sense in hex when you're splitting them up. These are single bits and they need to be 8 bits. Okay. Address 7 876544321. Store byte. Okay. And these are all in high Z state. I'll tell it to load so I can see what the data is. And if I clock it, boom, okay. That clocked on a single clock worked properly. There was no double clocking needed. So this is the RAM we're gonna use because the other shit is fucked. And it comes with a load. Okay, so I will just let me just go in here and get rid of this. Apply. Clock it. Put back in the 21. Okay, so now let's see what happens if we want to write a half. Okay, so we want to write a half. Yeah, it's real nice. So I want to write a half, but the address isn't aligned, so none of the stores are true. The only way I'm going to be able to write a half is if I'm aligned on 0, 0 or 1, 0, which now these aren't labeled anymore. But so if I align my address here, the last two bits on 0, 0, apply, you'll see that now I'm able to store, and the two that are going to store are here and here. Now this one should get 21, and this one should get 43. Nice. Okay, now the other way for this to happen is instead of address 4, where that's 0, 0, we make that 1, 0, 6, and now it should be storing to these two, which it is. And now the data in here, this should be 21. Oof. And that should be 43. Okay, so that's working. Why isn't 21 coming through here? Huh. Is this hooked to the wrong thing? Oh, nothing's coming through here when we're loading a half. Oh yeah, I fucked up. I need another. Okay, so the condition we're trying to do, we're trying to store a half at address 6 of this data. Okay, so let's remember that. I'm going to write it in chat. Store half at address 6 of 0x6754321. Alright, I wrote it in chat, so I don't forget the condition that we're trying to replicate here after I fix it. Hopefully fix it. Okay, so we'll stop it. We will move this over like so. I don't want to be such a degenerate with that fucking wire like that, so Control Delete. Damn. Oof. Oh, okay. I don't know what I pressed, but it just zoomed me out. Thank God. I thought I undid something. Okay. So I need another condition here that allows 21. That allows the low byte in. So we need 3 inputs on this. Shift that over. And now we gotta allow the low byte in. Oh yeah, 1, 2. Yeah, I did it on every other one but this one. Wow, okay. And then when half is true, that's what gets loaded. This should have fixed it. Save, run it. Okay, so the condition was half address 6. Data in was 8674431. trying to click store. Okay, data in 4321. Nice. I think that's working now. So now if I clock this, we'll see 4321 there. Cool. Okay. Now let's say we wanted to write a word. The only way we can write a word, we can't write a word at this current address. Oh. Oh boy. This can only, okay. I see an issue. So this can only be true when we're 0 aligned. So when the decoder is at 0 and okay, so that should work now. So we're going to say word at address 6, data in 8675431, store, load it. Okay, so now that's working properly because now we're saying we're trying to store a word to address 6, and address 6 is like you can imagine this is 4, 5, 6, 7. And so you can't store 4 bytes when you only have 1 byte above with the current one there. You'd have to be 0 aligned. So the only way this will work is if you change your address here to the bottom 2 bits being 0. Now you see the store comes true, and if I were to clock it, 8765, fuck, not 43, but 21. So now we need to figure out why 43 isn't coming through here. Now 43 isn't coming through here. Four three needs to come through here from the word oh, what the fuck? Yeah. Word is where each one takes its own. So I need to make 3. Actually, Control Z, Control Z. Okay, actually, all I want to do is say 43 here, or this one should come through not only on half, but on word too. Like that. So now if we go back, oh, that's just a 1-bit. So now let's try this again. I'm going to store a word at address 4 of 8765431. Yo, what up, Lulu? Thanks for stopping in. I'm gonna click store, load. Okay, so when I click this, there should be 43, 21, 65, 87. So if I clock this, 1, 2, 3, 4, 5, 6, 7, 8. Nice. Okay, so there is the control logic so far. For storing, I just want to test it out a little bit more. If I say store byte at address 4, this is 0, 1, 2, 3, so a 1 should be here. So it should select this one at address 1. If I were to, oh yeah, I am at byte. Yeah, that's what it's doing. It's telling it to store here, and it'll store 21 there. If I go, say, to address 5, I can now overwrite 21 there by saying clock. Oof. That is wrong. Oof. What did I do? Yep. Yep, I only made things worse by that fix. That's why I bug tested. So we're going to need 3 inputs there. Yeah, I did. I deleted some of those. Okay, so this has to take the word control signal, and we'll take its respective bit position, which is okay. Now let's try this again. If I want to write a byte to address 5 of 1865. What the fuck? I'm saying, how is this 63? How are both? What did I do? Oh. God damn it. Byte at address 5. 8765421. Store, load, clock. There we go. There we go. Fucking finally. Okay. And so now I should be able to move that around. I should be able to put that at address 4. Clock. I should be able to put 21 at each one of those. 6. Okay. Clock. Oh. There we go. 7. Okay. Clock. Okay, cool. So that's working. I was able to put 21 there in each one of those spots. I was able to write a byte to any one of those positions. Now if I want to write a half, I could say I'll write a half to there, and that's going to write a half to these 2 low bytes, so it's going to write 4321 there. Oof, why did the output change? I thought I had 21. What? Why did that? Let's look at that again. Clock. Oh, I'm dumb. It's because the address that I'm loading from is the current address here. Duh. It loads. You don't get a separate load address and input address. The load is the address. Yeah. Yeah, David, as you're saying that, I'm realizing it, but there's a 30-second stream delay, so that means you realized it first, so nice. Oh man, I'm dumb. Okay, so nothing fishy was going on there. Alright, so let me go back to a half. So I'm gonna write a half, 200 0. So I should get 4321 there. Nice. In address 1, it shouldn't allow me to do anything. So no stores are true. So now if I put it on just 2 and apply, okay. And now when I clock it, it'll put 4321 there. So now in my whole word, I have 2 of the same bytes, or 2 of the same halves. Yeah, halves in the same word. Okay, and then now for the just to double check to make sure I didn't screw anything. Now writing the word should write 87654321 there. When I'm allowed aligned on the 0 boundary there. So if I were to clock that, boom, 87654321. Okay. Stop. Control S. So far, the input and writing works. So, small round of applause. Now we just have to work on the other half of it. You know, no big deal. It only took 2.5 hours for me to figure out this fucking logic here. Jesus, and it's only possible too because I'm talking through it with David. It's like streaming's so nice because people talk and will tell you like their ideas. Great, because I need ideas. Now just to clean up some of this and make it look a little less janky, now that we know it works, I'm gonna make it look better. Hi Kleb, thanks for joining. Wow, Kleb, I haven't seen you in a while. Yeah, I hope you're doing well. I wish I could make this a little better. Yeah, I can. Yeah, I don't know how to actually, like, I don't know what kind of tests digital has built in, but if it's a simulation and the simulation works like as it should and the component, like all I have to do is just test the base workings of the component like I did there and just make sure it works for like a few of the cases. I'm not going to have to test every address of the RAM to make sure it's not working at certain addresses because it's a simulation and it's better. It's like in the real, I think those tests are more like if you were needing to use this in the real world and then test it in the real world. Like if you were writing this shit to an FPGA, because I don't know if you know this, but yeah, you can go to File and export it straight to VHDL or Verilog your circuit and upload that into your dev board. But yeah, it's a good idea to keep those in mind just in case I do need to use them. It's kind of annoying me how all these are on a straight line and then these ones are like not. You're a software engineer, so when you make something, you make tests for different scenarios. But oh yeah. Well, software never works as intended, but hardware it's a little different. So see, for instance, well, hardware also doesn't always work as intended. That's why in the real world you do have to run tests in the software. That's why in software in the real world you run tests, but the simulation here, you're assuming is perfect state. Like there's no like delay in the components, it's just computation time, and so it's just cycles that it has to take per component, like, so it doesn't actually calculate delay properly and shit like that. Like in the real world, I'm building like a test board for a bunch of fiber optic. There's 3 test boards that the customer has. Their data capture board, which pulls data from their computer. The data capture board then sends the data via low voltage differential signal to a fiber optic transmitter board. That transmitter board then has 29 parallel fiber optic cables that go to a fiber optic receiver board, and that receiver board then brings that data back in through a single-ended cable. So my board is connecting between that output to input system and generating data like it's the computer, and then checking that the simulated data that it sent was, or the data that it sent, not simulated, the actual data that it was sent is the data that it received and that they match. So like that's an example of me in the real world, like at work, like that as my job, like verifying boards, you know, because stuff doesn't always work as intended. So when you produce a circuit board, you want to test it to make sure that that the circuit board you built is going to work. You're not really testing the logic inside at that point. You're testing, is it soldered correctly? You know, is there shorts and stuff like that? If I send out this bit, is there 3 bits on at the output? Is there a short somewhere? You know, it's more like at the board level there. Yeah, I can, if I go to Discord, general, oh, that's a sexy car. So if I scroll up far enough here through all the crap, actually let me just search from the wild. Why is that? Disable. Contains image. Oh boy, give me a second here. Here we go. So I don't know if if that's about to pop up on stream, or it is up on stream, but I'm watching my live stream to see when it pops up. Here's that board. There's the backside. And here's like that, how it interacts with the customer boards. So like my board is here, and then these are the customer boards. You can see the fiber optic isolation there. And I have to manage all the clock delays because there's like 500 nanoseconds of delay all the way through the system back, and we're running at 10 megahertz, so yeah, you need to worry about those delays at that speed. And yeah, you can see in here it's like XORing and whatnot. So all this logic inside here is done inside CPLDs, which I program using digital, and I design the logic in digital. Anyway, yeah, everybody should join my Discord. Also, if you're still watching and you haven't joined yet, the link should be in the description of this video, I think. Down there where I throw all the social medias out. I wonder how far this could be brought in. That's probably about it. Yeah, that's probably as compact as I'm going to be able to get that right there. Save that. Oh yeah, I use digital all the time. Like I like block design. I don't like writing code. I don't like having to visualize how code flows. I like being able to look and test my circuit, like in something like this, and then it literally just exports VHDL, and not only that, but digital is natively compatible with the CPLDs that I'm using at work, which are literally the latest greatest CPLDs on the market, the ATF 15XX series. So you can get them the 1502s all the way up to 1508s. That's so there's 1504s, 1506, 1508. And at work I'm using the 1508, which is 100 pins output. It's like 84 of those pins are I/O. The rest are like power, ground, and like clock pins, and like the programming pins for it. So like I basically have 84 input outputs that I can control, that are programmable and run at, you know, I'm running them at 10 megahertz. So and I'm using two because if I use just one for all of it, I would overflow and fill up all the logic inside of a single one. So I split it up into two different CPLDs. One does address and one does data stuff. But in an FPGA that's much more powerful, you could put it all in a single FPGA. The CPLD is nice though because it has faster power on properties, because it's done through like logic tables, not like lookups, but like PALs and whatnot. Anyway, so now we got to get back onto getting this to work. Let's see what fucked up. Okay, nothing fucked up. Cool. So now let's say we want to load. Oh god. Oh god, this is gonna be cancer. Get rid of all the loads going in everywhere. Okay, I'm gonna kind of split my logic up like this. I'm gonna run my load pins signals down. You mean the load? Or same logic as the store? Oh. Yeah. Yeah, I see what you mean. So we're gonna need triple OR gates. Oh god. I shouldn't have compacted this. Okay, here's what I can do. I can just send the low 2 bits over and re-decode them over here. It's a 2-bit decoder. I'm not using that many resources for a 2-bit decoder, so I'm not too worried about it. Okay, so now I'll just tap off some buses. Oh, shit. So we know. Okay, fuck. Okay. Just like on the input, there was store and data in that we had to take care of separately, but they were both on the input and it was very confusing. We have to take care of data out and load signals. Data out will configure how the bus combines the bits, and load will configure which banks actually load. Okay, so what do I want to do first? Let's take data out and let's deal with data out first. I'm going to pull this down. Oops. It's basically this in reverse. So we're going to delete those. Yikes. Can you rotate the whole thing? No, you can't. Okay, so yeah, that's not useful. Okay, so you can read. Okay, so what we're gonna do. You can read. I'm gonna turn the outputs 90 degrees. So watch this. You're gonna be able to read a byte. Okay, David. I'll see you in a bit. You could read a low byte from each one of these. I just had to hack up a loogie. I didn't want to do that with my freaking volume turned up. Deafen you all. Okay. So, we could read a byte out to there. Then if you were to read a half, that would be the low, and then this would be there, or that would be the low, and this would be there. And then the word. Like that. components, IO, splitter, wires, on wires, splitter merger. Input splitting 8, output 32, get rid of that stupid sign. Okay. So the high one will go there. And we'll put components, ground. This is 8 bits. Okay, so we have so this is going to be read word. So I'm going to need data bits 8. Okay. Control C. Okay, so that's load word. Control C, Control V. Oh, what am I doing? I had it right. Hey, welcome back, dude. So here's my progress so far on the reads. So right now, I'm saying for the read word, because that's the easiest logic for me right now, just to do first. If we're reading a word, we're going to say take the byte out of each one of these and assign it. So this is 0, 0. So the byte from here will come in here and fill the low 8 bits. And this one here fills the next 8 bits above that, and that one there fills the next 8 bits above that, and then that fills the next 8 bits above that. I should probably label these RAMs. 0, 0, 0, 1, 0. Okay. So now, I'm just going to slide these guys down a bit. Now when I load a half, either this one or this one will have, yeah, because I'll only ever load, the load signal will ever come to this one or this one at a time. And so I will be able to just take either this one and ORed with this one. So I'm just going to move this over, give that 3 inputs. So now when I load a half, oh shit, I'm dumb. Delete, control, delete, bring that back, control C, control V, control V. Okay. Nope. These don't get connected together. So let's load half. Oh yeah, both of those would get connected together, wouldn't they? Yes. Because that's load half. And only ever one of those will be on at a time. So this is load. I gotta continue this bus down. So when I say word, it'll only allow that through and output. Gotta pull this down more. Yeah, so now when I say load half, it's gonna pick that one and send it to the high byte there. And then I need 3 inputs here. And then this is gonna be take I'll take this guy and that guy, and then these or together onto this. Okay, we're almost there. So now this is half, which is the middle one. Okay. So we have word and half. Now if we load a byte, oh wait, I'm doing it different. How many? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. I only have 9 up there, and I have 8 here so far. What am I doing different? I'm saying when it's a byte, it selects that out of, oh. Maybe I'm thinking of this wrong. Yeah, let me take another hit of the bomb. Think about this for another second. So the data outputs, how is this going to work? Yeah, but what I'm contemplating is, you see how I use this little decoder right here that simplified the logic? So that what it does is it says, like, take, if a half is true and it's aligned, then, you know, send it through, like, whatever. I should probably do the same thing here, so I'm not, otherwise I'm going to need a lot more muxes now for the rest of this down here. I'm trying to reduce the amount of muxes that I think I'm going to need. So maybe the more proper way to do it would be to say, when word is true, see, the byte condition here, where it just does everything here already, is the word condition here. So that's fine. The half condition has to be aligned the half condition can say if I'm aligned on either one of those or that, then allow a load, because I don't want to load if I'm not aligned. Yes. Yes, okay. I'm going to leave this logic for now, but I'm going to rebuild with the new. So I'm going to say Can't you take the control signals after the decode and use them in the muxes at the bottom? Right, but then you see how many more muxes I'm using? I would need more muxes. Like, I'm using 9 muxes here to control handling all the input splitting. Why can't I use the same amount of muxes to handle the output splitting? Like, I can throw more muxes at the problem. Don't get me wrong, I just don't want to. Even though they're in parallel, I'm just not going to slow anything down. It's just extra complexity that doesn't need to be there. So we're going to say if 0 or 2 is true, and we're doing half there, then we're aligned. And if we're aligned, then we should how did I do this? I have 3. So it's probably going to have to be C, Control V. Okay, yeah, let's undo that. Think this through again a little better. A little bit less confusing wiring. So I'm saying for Word, I should be able to select. No. So Word comes in and tells it what to do, which is grab the top 8 from here, next 8 from there, next 8 from there, and next 8 from there. Then it says half. So if the address is a 0 or a 1, F is taking that there. Okay. So I gotta do the same thing on half. I have to take oh, so I was doing it right. There's no way around it. Yeah. Fuck. So the high half bit will be here, and low half would be there. Oh shit. And that'd be the other high half. And the low half would be and this low half would be that one. Whatever. I guess I can't get around that. Yeah, I don't know if that's possible. Split them up. So this makes it so when you're loading a half and you're aligned, it'll put that on the, okay. Or when the address is aligned, it'll do the output properly. Now byte, you have to stick it onto the 0th bit. I don't know, we're gonna need a lot. Okay. What the fuck am I gonna do? So now we say we load a byte. The address doesn't have to be aligned to put the byte anywhere. Oh, but the address had to be aligned to put the word down. So this word signal, this word control, this has to be aligned. On 0 and on that. Oh. This one is word. This one is half. Now I have to do byte. I was just fixing up the the word signal here. The control for it should only be true when I'm 0 aligned. So when the address is 0 aligned, word is good. And then the address doesn't care for any alignment for byte. So now this byte signal can come down here, and it can tap off. So we're gonna need to, yeah. So I could say yes, and so I just grab all 4 of them. Oh, you're right. I can just can I just OR them? Or do I need an enable for the byte before just ORing them into this? So I can make that 5 instead. Oof. Right, when I send the load signal in, it would only load one at a time. The other one would be high impedance states, so it wouldn't backflow and fuck with it. So I should be able to just OR them all together and use a single mux. So now, yes, so 8, 9, 8, 9. See, that's that. I knew that. I was like, why do we have more than we need? And then that means I could redo how I did these up here too. That was the, yeah, see, talking to people in chat, especially you, makes me think about things I didn't think about actually before. Because now what I can do is, instead of using the OR gates there and using twice as many muxes here, I can now do the same trick, where instead of, because here only ever one of those will be true at a time, oh shit, I connected it. Control Z. Why isn't it not undoing? Edit, undo. Since only ever one of those will be true at a time on that. And then on load halves, only one half or the bottom half will be true at a time. I could say take the bottom one, fuck, how am I gonna do this? Say take this bottom one here. Okay, so here if I do Control C, Control since only either this one or that one will be true when I'm loading a half, and that's the bottom, I can make sure that I don't need this then. And I can come into there like that. Oh no. So it has to come like that. There we go. So I reduced that. Now I can reduce another one of these here. Yeah, I still need the mux. This only needs 3 inputs now. Yes, this is so much better. We're reducing the logic. Now that makes a lot more sense to me. I'm going to flip the position. Okay. That's kind of beautiful. Not gonna lie, kind of nice. Is it not in the description of my video? It is not. Okay, let me put it in the description real quick. Alright, you might have to refresh the stream to get the updated description, but check the description, and you should see a website in it. But if not, I will post it in chat as well. There you go. Okay, I think that's as simplified as this can get. And I don't, can this get any more simplified? I'm starting to think this could have been simplified. But not only ever one of those would be high at a time. Yeah, I'm just going to leave that logic alone and enjoy the fact that this is much more reduced. Right. Yeah, I like that this is like 4, 2, 1 like that too. It's very satisfying. Powers of 2. Components, I/O, output, 32 bits, data out, and hex. Controls. Okay. So I don't think we'll be fucked with anything too much now. In fact, I'm not sure, but we can just do some testing. I hate how that deleted all those wires. Control components, input, load. Can we run this? Fuck. Ah, fuck. That should have been 8, not 32. Okay, let me just test this out again. We're at a byte, address 7, store. Seems to not have fucked anything. Oh, but when load is off, what the fuck is going on? We've got a faggy delight coming through. Where is that value generated from? Where is this value coming from? FD? Which one of these values is generating FD? Oh, it has no idea what to generate because it's high impedance state. Oh, I'm telling it to load a byte from address 7. Yeah, it's just because it's high impedance and it doesn't know what to do. And I need to pull everything low. Components, I/O, wires. Pull down resistor. Rotate 180. No, fuck. Okay, so hopefully now, yeah, when that's not being loaded now, instead of high Z state, it's pulled to 0. So now, hopefully if I eight seven six five four three two one. Okay, cool. You're right, I can't, but as long as the other ones have zeros, and I only wrote 21 to a single spot. See how 21 isn't on any of those other ones? Because I only wrote a single byte of it. I didn't write it to any other, because I knew that was an issue. I was just I just wanted to make sure that my bus alignment here was correct. Give me 1 second. Okay. Yeah, so now we can start adding the logic for the actual load. So what we've done so far is we've done it's just like we have the input logic here that configures the input bus. We've done the output logic that configures the output bus. But now we've also done over here the input logic that configures like the store. Now we have to do the input logic that configures the load here. And we still have 3 people concurrently watching, which is pretty nice. So congratulations if you're still watching this far. I don't know if it counts me as a viewer because I don't have it open in another tab. I'm viewing it through the stream thing. It shows me, so I don't know if that counts me in that viewer count or not. It would be kind of dumb if it did. Okay, but now that we know that this is still working, we haven't broken anything. Yeah, it's gonna be similar to the store. Okay, so I will get rid of this. I've got to sneeze, oh no. Thanks, David. Okay, yeah, so let's figure this out. Speaking of which, my box empty now. Great. Oh man, so the load condition, we have to look at how load. So I'm gonna do this shit. I'm gonna basically Control C, Control V. Okay, just like how we did that for the store, we'll do the same thing for the load. So now what's the easiest load? The easiest load is the word. The easiest load is the word. Because the bird is the word. Bird's the, no, fuck. There. That's a little neater. Not really. Just stalling. Okay, word. When word is true and load is true, we will enable load. We will enable load of all 4. Yes, okay, yeah, this isn't hard. This isn't hard at all. So advanced, rotate 270, fuck me, 90. Stupid ass wide shape. And we're gonna say, when we load a word, we're gonna load all of them. So you're saying just copy? I don't know if that'll work. Oh, it will. Actually, it's the same. Well, I still have to rebuild it because I have to rotate it by 90 degrees. But I could still use, I think I can use basically the same logic. So I'm saying when I'm storing a word, and I'm zero aligned, put on all those. You know, it's only single gate, it's not the whole selection. That's the issue. So if I'm zero aligned, I can do that. Yeah, watch. Oh wait, no it is. What the fuck? But will it mirror it though? Control V M. No. What would be the mirror? If R is rotate, what would be mirror? So now if I load a half, I see. So now if I load a half and the 0 is true, so now 1, 2, 4. Oh yeah, it's the same power of 2. Yeah, 1, 2, 4. 1, 2, 4. Yeah, okay, so now I'm gonna do 1, 2, 4. Because now basically I need to say if it is a half and it's aligned on 0, or if it's a half and it's aligned on 1. If it's a half and it's aligned on 0, then I'm going to read these two. So if I load a half, and it's aligned on 0, This one is aligned on 2. Okay, so this is going to load the bottom 2 here. And then this will load the top 2. Like that. So there's our 4 connections there. Now loading a byte, we have to check for each individual one. So you say 0.1, 2, 3. And 3 input. Oh, not 33. That's gonna fuck everything up. Okay. And this and that OR gate is like the opposite logic. Oh, it's the same. It's literally the same logic as that right there. Cool. Just built in a different manner instead of like 90 degrees rotated. Like these 4 is 90 degrees rotated, where these 4 are just right there. But that should be the same thing now. And fingers crossed. Oh yikes, he might. Not all circuits have the same. What the fuck? Oh shit. Control Z. Control Z. Edit. That's a shame. And it works. Well, it's running. I don't know if it works yet. Nothing on the data output. Alright, let's try this. Address. We'll leave it at 0. Data in 8675432. we're going to store a word at address 0. And I'm also going to want to load at the same time. Cool. When I stop loading, it goes away. Okay, so the first 4 bytes, 0 through 3, have been written to. So I will go to 4, and I will write, I will write a half at 4, and then a half at 6. So that I will write, so we'll have, in the low 3 bytes, we'll have this, and then in the 3 byte, in the low 4 byte, in 4 bytes, we'll have that, and the 4 bytes above this will have 2 copies of 4321 instead of the top of it right here. Sorry, that was hard to spit out. So first we'll write to 4. If I load to see what happens, we'll clock. And then if I now write to 6, okay, and store, and we read to see what happens, and I clock, cool. And now if I leave the read on there, get rid of the store, and now change this address back to 4, you'll see it now go 4321, 4321. There, well, it should have. Oh, because I'm still loading a half. So now if I go to, oh, word, there we go. 4321, 4321. And I could say load that, load the half there, or I could say just load the single byte there, which would just be the 21. So boom, the byte addressable RAM is working. Well, guys, we just built byte addressable RAM. So we have a shit ton of RAM. 2 to the 26 bytes. 2 to the 24 words. So 2 to the 24, let me do that math. 2 to the 24 is, we have 16 million words. So if I multiply that by 4, that's 67 million bytes. So we have 16 million words here of just data memory. So we're going to be using this for our data memory in our CPU. And what's nice now that I can load bytes, half, and words is when I want to do caching, and my cache needs to load a byte, load a half, load a word, or whatever like that, I can do that. And then we could fuck around on caching later after we build the 5-stage pipeline CPU. But this is kind of nice. This is much neater than every other byte addressable RAM I've made. In fact, let's show the other one. This one's simple, but it's just not clean compared to this one. I feel like this is much cleaner in terms of logic and what's going on. This was very not fun to do. This was a lot better, I feel like. Debating on whether or not I should have flipped these select inputs, but oh well. Yeah, I think that's it for the stream, guys. Thanks for watching. It's 5:50. You can even still deduplicate the store and load logic. What do you mean? Just deduplicate. Where? Wait, David. Deduplicate what store and load logic? Or do you see that's duplicated? What do you mean it's just a little different with the... What you're trying to say, use the same load and store logic? And just say whether or not it goes to store or load? And just use the same logic? So instead of having it built redundant like this, alright, here, we'll file save. Before I go, we'll make a new circuit called byte address RAM reduced. So now this is saved as that byte logic RAM reduced. So you're saying this store can go to the load input here. Components. Oh, but then I'd have to get... yeah, but then I'd have to put this logic here at the... I'd have to put these AND gates, like you're saying, at the input of the store. Then the other AND gates would go at the input of the load. Yes. Yes. Let's do that. Good call, good call. See? I didn't want to leave if you had a great idea, so that's a good idea. I see what you're saying. Let's do it and see how it works. I like reducing logic. So... and so when store is true, so yeah, if we put the store logic, oof. C control V. Okay. And then the load signal. Fuck. Control C, Control V, and 90. Or 0. I think it's 0. Control C, Control V. Oof. Okay, so when the load signal is true, That's not the load. That's the. Oh yeah, that is, but it's not the master load control. This is going to be the master load. This has to come from this guy there. Generate that load. There. And run. See what's broken. Of course, I need to hook it up to the fucking load signal. Alright, now let's see what happens. So, data in 867 4 3 2 1. Store, load, and clock it. Oh, I'm not telling it to write a word. And clock it. And now I will go to address 4. Okay, tell it to write a half. Clock it. Go to address 6. Tell it to write a half. Clock it. Go back to 4. Tell it to read a word. Cool. Yep, your method works. Very nice. Yeah, that's you like made this thing way simpler than I would have made it. So thank you for being in the live stream today. I appreciate it. And yeah, now I think I'm gonna end it. So have a good night. I don't know if you guys are interested in UFC fights, but they're tonight, probably starting right about now. So yeah, if you're looking for something else to do for the rest of your night, you can go watch the UFC fights if you're into that. Anyway, I can export this file and upload it onto the description of this video. Anyway, till next time, peace out, guys.